dividing free stream and this source flow. Okay, so this the streamline is called dividing streamline. Okay, and you know the properties of streamline. Streamline will have only the tangential velocity, right? It won't have the normal velocity. So there is no flow across this streamline. Okay, so outside it is full of free stream, inside it is full of source flow. Then what we are doing, we are replacing this internal flow with a solid body. So we are assuming internally we have solid body, then we can simulate flow over the half Rankine oval. Okay, so we have to prove this line is a streamline. That means it should have only the tangential velocity and normal velocity should be 0. So everywhere in the potential flow, we will use this dividing streamline condition. So here also we are going to use the dividing streamline. That is, we have to prove this line is the dividing streamline and it doesn't have the normal velocity. That's what we are going to prove. Okay, so I mentioned 4 assumptions and 2 conditions. One is dividing streamline conditions, that is normal velocity across that line is 0. Then Kutter's trailing edge conditions. At the trailing edge point, strength of the small vortex is 0. Is that clear? Any doubt in this? So if you are writing the final exam in the offline mode, these are all the important role marks. Okay. So using these assumptions and conditions, what you are going to find? First, we are going to find strength of these small vortices, small gamma, then strength of the complete vortex sheet, capital gamma. Once we know the capital gamma, we can find the lift. Last class only we discussed L is equal to rho v gamma using Kutarz-Zagorski theorem. Once we know the lift, we can find CL. Once we know the force, we can find moment acting on that any point. Mostly we will find moment about the leading edge. Once we know the moment, we can find coefficient of moment. Okay, once you know force, moment, etc. and all, we can find center of pressure location, even aerodynamic center, etc. and all. This is the procedure. Is it clear? First small gamma, then capital gamma, then lift, then moment, then CL, CM, then XCP. These are all the parameters. We are going to find it now in this derivation. Okay. So this is our final model. So X and Z axis I am taking. So the flow velocity is V infinity. Airfoil is at an angle of attack alpha, and chord length varies from 0 to S. Camber length varies from 0 to S. Okay. So first we have to apply this dividing streamline condition, that is normal velocity is 0, and you see this normal velocity at any point is due to the 2 sources. One is this free stream, another one is due to this vortex. Okay, at any point if you find the normal velocity on this camber line, it is due to the 2 components. One is due to the free stream velocity, another one is due to this vortex velocity. Okay, so the normal component induced on this camber line due to the free stream is V infinity n. Normal component of velocity induced on this camber line due to the vortex sheet is W. I am taking. Is it clear? Somebody reply. I don't know. Is there any connectivity issue or you are sleeping? Hello?
Yes, sir.
Yes, sir.
Okay. So first condition is dividing streamline condition. Normal velocity is 0. Normal velocity is due to the free stream and vortex sheet. So first we will find the normal component due to the free stream. Okay, before that one introductory topic. So in fluid dynamics, that is in the potential flow, so for all the object, we are using polar coordinate. For example, in the experiment also, you see, for the cylinder, we are not finding a different dia or different arc length. We are finding property for different theta only, right? 0 to 180 degree. So for whatever the object, the potential flow will use only the polar coordinate. Even for the aerofoil, so we won't find the property for different chord length. We will find it from 0 to 180 degree only. So everywhere the potential flow uses polar coordinate. But here, whatever we study in the aerofoil, so we have taken chord length 0 to C, camber length 0 to S, like that only we have taken. Cartesian coordinate we have taken. So we have to convert this Cartesian coordinate into polar coordinate. So for that, we are using these equations. X is equal to C by 2, 1 minus cos theta. Now I'll explain how to get this relation. So using this, we are going to do the coordinate transformation. This is the first step. So this is the chord length, varies from 0 to C. Okay, in between it is Z by 2. Okay, so this is the chord length of the aerofoil. 0 to C it varies. So in center point means it will be C by 2. So normally we will take at some distance at X position what is the pressure, like that we will find it, right? So we are going to convert this X in terms of theta. Okay, so to convert that, I am drawing one semicircle on it. Okay, if you draw a semicircle, you know what is the radius, it will be C by 2. Is that clear? So this is the chord line, 0 to C it varies. Center point if you take it is C by 2. So to convert that coordinate point from Cartesian to polar coordinate, I am drawing on semicircle. Okay, and the radius of the semicircle will be C by 2. Up to that clear, right?
Yes, sir.
Okay. Now assume I am taking one random point on the chord line, which is X. Now I want to write that X in terms of theta. Okay. So this is my distance reference length X. Just draw one vertical line and we will get to an intersection point in the semicircle. Okay. And from that draw another one straight line, inclined line to the center point. We know the radius is C by 2 and assume the angle is theta. Okay, now I can write this distance as C by 2 cos theta. Okay, so write again. So this is the airfoil chord, 0 to C. So I have drawn one semicircle. So the radius is C by 2. So this is the reference length I have taken in the chord line X. Okay, so now I want to convert this X in terms of theta. So what I am doing, I am just drawing one vertical line from the X distance. Okay, so I am getting one intersection point on the semicircle. Just draw another inclined line towards the center. I know this distance is C by 2 because it is a radius. Anywhere you draw, it will be the radius. And I am taking this angle is theta. So I am taking theta in the clockwise direction. Now I can write this distance, which is C by 2 cos theta. Okay, and this is X. And you know the overall length is C by 2. Okay, now I can write X is equal to C by 2 minus C by 2 cos theta. Is that correct? This X is equal to C by 2 minus C by 2 cos theta. You take C by 2 outside, you'll get 1 minus cos theta. So this is the relation which converts X coordinate to theta coordinate. Is that clear?
Yes.
Okay. In many books, they didn't explain this concept. Straight away, they are given X is equal to C by 2 1 minus cos theta. Okay. Similarly, if I have taken one point here, right, you may take another one point. So this erase it. Okay, this is the chord length. Now I am taking my reference point here. Okay, I am taking that length as x1. Okay, here it is x, x1, x2, like that I can take n number of divisions. Okay, so assume this point is x1. So same procedure, we have to draw one straight line. You will get an intersection point, and from that you have to draw one straight line to the center point. So this radius is C by 2. And as I mentioned, we are taking theta from the clockwise direction. So this is my theta. Just I'm taking theta as theta 1 because here I have taken x1, so theta also theta 1. Okay. For example, here the theta is 10 degree. For x, corresponding theta is 10 degree means for x1 it may be 90 degree or 100 degree something. Okay, so for x1 I'm getting theta 1. Then this side theta, if you take, it will be 180 minus theta 1, right? Is that clear? I will write again. I will write again. It is not. Okay, I will write again. 0 to c by 2. So this time I'm taking my reference point here. I'm denoting that as x1 because it is some other point. I can take some other point here. I can name it as x2. Like that I can take any x value. And this radius is c by 2. So this is my reference point. You have to draw one vertical line. You will get an intersection point. Join that intersection point to the center point. You know this radius is c by 2. Always take theta in the clockwise direction. Okay, so this I'm taking as theta 1. Then this angle will be 180 minus theta 1. So now I can write, see this distance, if you see, from the center point to this reference length, it will be c by 2 cos 180 minus theta 1. This we can write it as c by 2 cos theta 1. Is that correct? This small distance. So now I can write and see this distance. It is simply c by 2. Okay, this distance is c by 2. From here to here it is c by 2 cos theta 1. Now I can write x1 as c by 2 plus c by 2 cos theta 1. I think minus cos 180 minus theta is
minus cos theta.
Minus, right?
Yeah.
So this is minus. So here also you'll get minus. So you'll get c by 2 if you take outside, it will be 1 minus cos theta 1. x1 means. So previously we found x is equal to c by 2, 1 minus cos theta. Now it is x1. You will get c by 2, 1 minus cos theta 1. I can take any point on this chord line. For example, x3, x4, x5. You will get corresponding theta value. So this is the equation to do the coordinate transformation. Is it clear?
Yes.
So in the exam, you need to explain these things and all. Straight away, you can take this equation in the derivation. No need of this explanation. This is just for your understanding. The same thing already I created. C by 2 1 minus cos theta, c by 2 1 minus cos theta 1. Okay. So now, yeah. So we are trying to find normal velocity of this camber line, which is due to the free stream on the vortex sheet. First, we will find it for this free stream. Okay, so this is the camber line. I'm just taking one reference point on the camber line. So here I'm going to find normal velocity. Okay, that is normal velocity due to the free stream. This is the free stream flow direction. I'm just drawing one parallel line, free stream velocity. So this V infinity I can resolve into V infinity N and V infinity S. Okay, so this V infinity I'm resolving with respect to this reference area length. So the normal component is V infinity N, tangential component is V infinity S. Is that clear? I'm going to resolve this V infinity to two components, V infinity N and V infinity S. Is it clear?
Yes.
What we need is this V infinity N, and this is the camber line, and we can find the slope at different point on the airfoil. Okay, I'm taking the slope is theta, the small red color line I'm taking here. So you know this axis is x-axis. So dx, okay, this is dx. Then vertical axis is dz. So it is coming down, so it is minus dz. So now I can write tan theta is equal to minus dz by dx, and theta means tan inverse of minus dz by dx. Is it clear? Slope of the curve on this small reference line. So for this small length, I'm finding the slope. I'm taking the angle is theta. So this is dx, this is minus dz. Tan theta is equal to minus dz by dx. So theta is equal to tan inverse of minus dz by dx. So I found the theta. Okay, so our final aim is to find this V infinity n. So for this reference line, here I mentioned. So you know the slope is theta, okay, and this angle is alpha. You can see this is the chord line or horizontal line. This is the flow velocity. This is the angle of attack, and above also we will get the same angle, right? Opposite angles are equal. So here we are getting alpha. So this is slope theta. Above it is angle of attack. Is it clear? This theta and alpha.
Yes.
Okay. So now we can simply resolve. So V infinity n means it is V infinity sine alpha plus theta. If you want V infinity s, it will be V infinity cos alpha plus theta, right? But here we need only V infinity n. V infinity sine alpha plus theta. Theta also already we found it is tan inverse of minus dz by dx. Substitute. And we know the assumptions. Angle of attack is very small, camber also very small. Okay, in that case this slope will be very small, theta also very small. So sine theta tan theta is equal to theta. So instead of this tan theta, we are taking only the theta, and instead of this sine theta, we are taking only the theta. That is tan theta is equal to minus dz by dx. So if theta is very small, tan theta we can take it as theta. So theta is simply minus dz by dx. Okay, and sine theta also it is simply theta. So this we can write it as V infinity alpha plus theta. Okay, sine we cancel. Now V infinity alpha, instead of theta straight away we substitute minus dz by dx. That's it. So this is equal to the V infinity n. Is it clear?
Yes, sir.
Okay, so we found one component. Now we have to find the normal component due to the vortex sheet. So here you see the vortex sheet, the straight away placed on this chord line. Okay, so I'm taking one small distance dx. Okay, from the leading edge, the distance is x, and this small area induces the normal velocity at some other random point. I'm taking that as x1. You know, vortex will have the velocity in all direction, right? But here we are interested to find only the normal velocity. Okay, so it is producing the velocity in all direction, but we are interested to find only the normal component of the velocity. So this small section induces the normal velocity at some random point. Okay, so minus dw are taken. You see, for the normal vortex, this is the velocity formula we study. So strength is circulation, the radius is r, and tangential velocity is minus gamma divided by 2 pi r. Okay, and here we have taken one small distance, then the strength will be simply small gamma, velocity in this is just dv. So this equation for the small portion is dv is equal to gamma ds divided by 2 pi r. Okay, for this small section the strength is d gamma, which is gamma into ds, right? But here we have taken x. So it should be x. This is the general formula. So this general formula we can apply to this condition now. So instead of, so this is for general equations. So instead of dv, here we have taken w just to differentiate it. So it is dw is equal to minus strength is small gamma dx divided by 2 pi r. R means distance between the origin point and the point at which the velocity is acting. Okay, this is the r. So r here is x1 minus x. So I will repeat. So this already we studied. Velocity is minus gamma divided by 2 pi r. This is for complete vortex. And for the small section, this is the formula. dv is equal to minus gamma ds by 2 pi r. Apply this to this condition. So instead of v, I am taking w. So minus gamma, here I have taken x. So it is gamma ds divided by 2 pi. Now this is the distance r, which is x1 minus x. So this is the normal velocity induced by this small section. Then if you want to find the velocity induced by the complete vortex sheet, simply you have to integrate it. Okay, you have to integrate on both sides from 0 to c. So here it is overall velocity is w. Here integral 0 to c, same term. Okay, so now we found both terms, ws term and v infinity n term. Substitute, this is v infinity n, this is ws term. Just they rearranged, and this is called fundamental equation of thin airfoil theory. This they may ask in 6 marks. So writing the dividing streamline equation is the fundamental equation of thin airfoil theory. So simply we have to prove normal velocity is 0, but normal velocity is due to the free stream and vortex sheet. Is it clear? Or I will repeat it if you don't understand. So this formula already we discussed. So straight away I started. Any doubt up to this?
No, sir. This equation, what will be? Where will be we using this equation?
So this is the fundamental equation. From this equation only, we will find small gamma for different airfoils. From this fundamental equation, we will find small gamma, then capital gamma, then lift, then moment, etc., etc. and all.
Okay.
Okay. So in the 12 marks they ask, straight away you can start this equation. For example, write the force coefficient acting on the symmetrical airfoil means the derivation will start from this equation. Okay, 12 marks. You know to write these steps and all. Straight away you can start from this equation. But if they ask fundamental equation of thin airfoil theory, then you have to write this derivation. There are steps to find this v infinity n and ws.
Yes.
Okay. So this is the fundamental equation. Now we will see forces acting on the symmetrical airfoil. So this is the same equation, fundamental equation. So for symmetrical airfoil, already we assume it is very thin. It may be equal to this, like a thin flat plate. You know, for symmetrical airfoil, the slope is 0, right? Thin symmetrical airfoil means it will be like a thin flat plate. So for the flat plate, there is no camber, right? There is no slope. So d z by dx is 0. Then this term is 0. Is it clear? Only if the airfoil is like this, then we will get different theta. If it is a straight line, then there is no slope. Okay, slope will be 0. So here it will become a straight line. So slope is 0. This term is 0. Now this is our fundamental equation for the symmetrical airfoil. From here we are going to proceed. Is it clear?
Yes.
Okay. Now this is our main equation. So first step is doing the coordinate transformation from x to theta. So x is c by 2 1 minus cos theta, x1 is c by 2 1 minus cos theta 1. And if you differentiate this, you will get dx is equal to c by 2 sin theta d theta. Okay, now substitute all these terms in this equation 1. Okay, so instead of dx, I am taking c by 2 sin theta d theta. Instead of x1, I am taking c by 2 1 minus cos theta 1. Instead of x, I am taking so 1 minus cos theta. If you take minus inside, it will be minus 1 plus cos theta. And simplify, you will get this term. Okay, so instead of x, I'm substituting theta and simplifying. So from this equation is converted like this in terms of theta now. Here it is everywhere x, now it is everywhere theta. Is that clear? So these
Yes.
three, sorry, Delma.
Yes, sir. You asked me, is it clear? So,
Okay. So now from this we are going to proceed. Okay, so we found fundamental equation in terms of theta for symmetrical aerofoil. And here I have given the solution straight away. If you solve this, you will get gamma is equal to 2 alpha v infinity 1 plus cos theta by sin theta. And these steps are not necessary for the exam. And two ways they explain these steps. If you take fundamental of aerodynamics by Anderson, they proved, actually they didn't explain how to derive this step, but they explain how to verify this result. That is, if you substitute this gamma in the same equation, you will get LHS equal to RHS. Then the solution is correct, like that they proved. And if you take aerodynamics for engineering student by Horton and Carpenter, there they derived how to get these steps. So you can refer both books for understanding, but for the exam, these steps are not required. If you include these steps also, it will be like a 12 marks. Is that clear? In the exam also, straight away you can write the solution, but for understanding, you can refer the books. Is that okay? So normal integration only, but not simple integration. So if you want to get the steps, you refer Horton and Carpenter book, or for you can refer aerodynamics for fundamental of aerodynamics by Anderson for verifying this result. But both are not necessary for the exams. You can also straight away write the solution. Is that clear?
yeah.
Okay. So now we have the small gamma. Then second, we have to check whether this gamma is satisfying the Kutta condition or not. Okay, so Kutta condition means at the trailing edge, strength should be 0. Okay, so already we converted this into the theta coordinate. So the theta varies from 0 to pi. Okay, so that means theta at the trailing edge is pi. Okay, so take this equation. So everywhere instead of theta you have to substitute pi. So if you substitute cos pi is -1, sin pi is 0, it will form the 0 by 0 indeterminate form. Okay, you know, if it is indeterminate form, you have to use which rule? So you have to use L'Hopital or L'Hopital or L'Hospital, whatever you pronounce. That rule you have to use. That means you have to differentiate this again. If you differentiate, cos theta will be minus sin theta will be cos theta. Now if you apply again the theta value, sin 0, 0, 0 by everything is 0. We are getting gamma is equal to 0. So this solution satisfies the Kutta's condition. That means you will get only one solution. Is that clear?
Yes.
Okay. So at the trailing edge, the strength is 0, that we proved. So as I said, once you know the small gamma, we are going to find the capital gamma. You know the relation from the vertex sheet. Capital gamma is equal to integral 0 to c gamma dx, right? Capital gamma is equal to integral gamma dx. Gamma is given, and instead of dx we can write c by 2 sin theta d theta. Simplify, that is sin theta get cancelled, 2 get cancelled. Remaining will be V infinity alpha c integral 1 plus cos theta d theta. Now integrate and apply the limits. You will get this equation for capital gamma. Is that clear? So everywhere you are getting dx, that you have to convert it into theta. You should not forget. So this is the gamma equation, capital gamma equation. Okay, so this is the small gamma. Just we found it. And instead of dx, it is c by 2 sin theta d theta. Simplify, integrate, and apply the limits. You will get v infinity alpha c pi. So once you know this capital gamma, you can find the lift using Kutazakovsky theorem. Rho v gamma. Simply you have to multiply by rho v. So you can get the lift equation. What is meant by L dash? Anybody can say what is L dash?
Two-dimensional.
Sorry, ma?
Two-dimensional.
Yeah, good. L dash is for two-dimensional, but this is lift per unit span. Okay, 2D means there is no span. Unit span is there. So the proper definition of this L dash is lift per unit span. Okay, this is for two-dimensional. You are correct. So once you know lift, we can find the CL. L dash divided by half rho v square s, and here as it is 2D, it is simply C. Substitute and simplify, you will get CL is 2 pi alpha. Is that clear up to that? Okay. So hereafter it will be like this fully, full of derivations. Okay, so we found CL which is 2 pi alpha. Then we can find the lift slope also, which is dCl by d alpha. If we find, it will be 2 pi. Okay, if you differentiate this with respect to alpha, it is simply 2 pi radians power minus 1. Or in terms of theta degree for minus 1, if you rate, it will be around 0.1 or something. Okay, so lift equation is over. Now we'll go for the moment equation. The one break. Hello? Shall we proceed or we can take break? So remaining moment equation, then center of pressure. That's it. Shall we proceed?
Yes, sir.
So once you know the lift force, we can find the moment force. You see the drawback of this thin airfoil theory, we can find only lift and moment. We cannot find the drag. That is the drawback of this thin airfoil theory. Okay. So same the vortex sheet configuration I am taking. 0 to C or 0 to pi, it varies. So initially I am taking one small distance dx, where the strength is d gamma, which is gamma dx. Okay, everywhere it is x. Then, so we know the complete lift. First I am finding the lift for the small section, which is dl dash. That means rho v gamma. Here the strength is d gamma, and d gamma I can get it as small gamma dx. You can mistakenly written yes. Is it clear? On the thin airfoil, I am taking one small distance dx, where the strength is d gamma. Normally lift is rho v gamma. Okay, but here I am taking one small distance, so strength is d gamma, and lift is dl dash. That is rho v d gamma, and instead of d gamma, I am taking gamma dx. Is that clear? Lift for this small section. Any doubt in this? This for complete airfoil, this for one small section. Okay. Now assume this small force creates the moment at this about this leading edge point. Okay. So dm m dash le is equal to minus dl dash into x. Okay. Assume this small lift force induces the moment about this leading edge point. So force into distance anti-clockwise. So minus x dl dash. Now assume this is small section, right? The complete force acting on this complete rotor sheet induces the movement about this leading edge, and simply you have to integrate from 0 to c. Okay, for the small section it is dl, and for the complete section you have to integrate from 0 to c. Now this is the moment equation. Is it clear?
Yes, sir.
Okay. So with that we will proceed it further. Same equation I have done here. Moment created by the complete airfoil. So dl just now we derived, which is rho v d gamma. Instead of d gamma, you have taken small gamma dx. Okay, substitute here, and this is x, and rho v is constant. Take it outside. Remaining is x gamma dx. Okay, so again we have to do the coordinate transformation. Instead of x, we have to write c by 2 1 minus cos theta. Dx is c by 2 sin theta d theta, and gamma already we got it. Substitute, simplify, sin theta get cancelled, 2 get cancelled, c square by 2 you can take it outside. You will simplify, you will get this equation. Now you have to find value of this integration, 1 minus cos pi theta. Here I mentioned the steps. Final value is pi by 2. Instead of cos square, we can write 1 plus cos theta by 2. Then rearrange, apply the limits, you will get pi by 2. Okay, so instead of this, we have to substitute pi by 2. Solution of this integration. Substitute. This is our final moment about the leading edge. And what we need is the coefficient of moment. That means simply divided by half rho v squared sc. As it is 2d, area is c. So it means we will get c square. Is that clear?
Yes, sir.
Okay. Okay, so instead of m square, m dash le, substitute this equation, and bottom it is half rho v square c square. Simplify, we are getting some moment about leading edges. The coefficient of moment about leading edges pi alpha by 2. But I want to write this coefficient of moment in terms of CL, so later it will be useful. So I know CL equation for symmetrical airfoil, that is flat plate, it is 2 pi alpha. So I can write pi alpha is equal to CL by 2. So instead of this pi alpha, I can substitute CL by 2. So I will get moment about the coefficient of moment about leading edges CL by 4. Is it clear?
Yes.
Okay. So we found lift CL, moment CM, finally center of pressure location. Okay. So drag will be in the same symmetrical airfoil, means in the same line. It won't induce any moment about the leading edge. Only lift will induce the moment about this leading edge. And the drag we are not taking also in this calculation. We simplify like that. Okay. So we are finding moment about this leading edge, which is minus L dash into C XCP. You know, C is in terms of chord. Normally we'll tell only X. Okay, but here in terms of chord we are telling C XCP. So moment about this leading edges minus L dash C XCP, and we need coefficient of moment. So divide this by Q C square. Q you remember, I think, half rho V square, academic pressure. So divide by both sides. So this is equal to Cm the CC get cancelled, and this is equal to CL, and rearrange. So what we need is the center of pressure location. So XCP is equal to minus CM divided by CL, and instead of CM we can substitute CL by 4. If we cancel, we will getting only 1 by 4. Okay, so here if you mention, it will be 25% of the chord. Is it clear? Center of pressure derivation for flat plate or symmetrical airfoil. Okay, so what we understand is this center of pressure calculation has the constant value 1 by 4, 0.25. There is no alpha term, CL term and all. If there is any alpha term, then we can say as alpha changes, this XCP also will changes, either we can say. But now it is constant. So what do we understand? For the thin symmetrical airfoil or the flat plate, the XCP is fixed. Center of pressure location is fixed, and it is lies at the 25% of the chord. Okay, from this derivation, what we understood, for symmetrical airfoil or a thin symmetrical airfoil or flat plate, the center of pressure location is fixed because there is no variable here, and it is lies exactly at 25% of the chord.